Hey everybody, I thought we'd do a brief lecture here and a walkthrough on z-scores. So let's go ahead and do that. So, share our screen here. And I think we'll probably do a worksheet on that in this lecture, guys. So, all right, here we go. Okay, so z-scores, location of z-scores and distributions. So a z-score is basically a way to equalize the standard deviation. So if you remember chapters 1 through 4, I think 3 and 4 primarily, we talked about standard deviation. It's just a way of basically converting a standardized score. So some stuff we'll talk about today will be understanding the z-score as location in the distribution, transform the x value into a z-score, transform a z-score into an x value, and describe effects of standardizing a distribution, and transform scores to standardized distribution. So you want to remember the mean, that was our average. Now the mean makes sense in real life. I think I mentioned this before. It's always a good idea to go to like ONET, Salary.com, Glassdoor, Indeed, Department of Labor, and look up the average for the job that you have or will have, which is your mean, and ask for the mean or higher. Don't start at the bottom. There's absolutely a real world application of that. You also want to make sure you remember the standard deviation. Remember, the standard deviation is the square root of the variance, which is the sum of the squares over the n. And of course, basic algebra math review, that's in Appendix A. So one way we want to think about, identify and describe the location of every score in the distribution, standardize an entire distribution, take different distributions and make them equivalent and comparable. And z-scores, like I said, are also standard scores. So one way to think about a z-score is how you might compare the performance of a player in 1968 to one in 2000. We know that scoring was much lower in 1968. So if we simply looked at the raw batting averages or home runs hit, the player from 1968 would likely appear to be much worse. But if we standardize their scores by comparing them to the mean batting average or home runs hit in 1968 and 2000, we now end up with a common metric to compare the scores by how well they did relative to other players in that season. So this is figure 5.2, two distributions of exam scores. For both distributions, the mean is equal to 20. But for one distribution, the standard deviation is 2 and the other is 10. The relative position of your score, x equals 26, is very different for the two distributions. So the exact location of a z-score within a distribution is described by the z-score. The sign, plus or minus, tells whether the score is located above, positive, or below negative on the mean. I'll show you a graphical example in a moment. The number tells the distance between the score and the mean in terms of the number of standard deviations. So as you can see here, we have our mean right in the center there. That's the Greek mu. And then you have theta, and it's talking about the standard deviation. So as you go to the right of the mean of that bell curve there, +1, +2, those are your two standard deviations. -1, -2. Like I mentioned this before, those are used a lot of times with intelligence tests. Usually it's about 15 standard deviation points. Most people are around 100 for the mean. If you're 115, 130, 145, 160, you can do a lot more cognitively. If you're an 85 or a 70, you can do a lot less cognitively, at least in terms of what traditional intelligence scores are. So this is your formula. Z is equal to x minus the mean over theta, or the standard deviation. So z is equal to x, or the value, minus the mean over the standard deviation. The numerator is the deviation score. The denominator expresses deviation in standard deviation units. Remember that z-scores identify a specific location of a score in terms of deviations from the mean and relative to the standard deviation. So to determine a raw score, or x score, z is equal to, like I mentioned, x minus or the value, x is the value, minus the mean over the standard deviation, or theta. Therefore, x is equal to the mean plus the z-score times the standard deviation. And then you can algebraically solve for x to reveal that what the answer is. And the raw score is simply the population mean plus or minus if z is below the mean, z multiplied by the standard deviation. So computing z-scores for samples. Populations are the most common context for computing z-scores. It is possible to compute z-scores for samples. This indicates the relative position of the score in a sample, indicates the distance from the sample mean. The sample distribution can be transformed into a z-score, the same shape as the original distribution, and the same mean, or m, and standard deviations, or s, for sample statistics. So learning check, if we have a z-score equal to +1, that indicates the position and distribution in the following way: above the mean by 1 point, above the mean by a distance equal to 1 standard deviation, below the mean by 1 point, or below the mean by a distance equal to 1 standard deviation. So if you know, great. If you're not sure, maybe pause me or take a moment. And the answer is a z-score of z equal to 1 or 1.00, same thing, indicates the position and the distribution of above the mean by a distance equal to 1 standard deviation. So now let's see if you can decide if each of the following statements are true or false. True or false, a negative z-score always indicates a location below the mean. And true or false, a score close to the mean has a z-score close to 1. Think about that. Pause me if you need to. So the first answer is true. The sign indicates that the score is below the mean. And the second one is false. Scores quite close to the mean have z-scores close to 0, because we're talking about how it deviates from the mean. Some other relationships between a z, x, and the mean and standard deviation. A z-score establishes a relationship between the raw score, the mean, and the standard deviation. When given a mean, raw score, and z-score, you can compute the standard deviation. When given the standard deviation, raw score, and z-score, you can compute the mean. So here's a visual representation of the question right here. If two standard deviations correspond to a 6-point distance, then one standard deviation must equal 3 points. So figure 5.5, this is a visual representation of the question of example 5.7. The 12-point distance from 42 to 54 corresponds to 3 standard deviations. Therefore, the standard deviation must be S, or standard deviation, is equal to 4. Also, the score x equals 42 is below the mean by 1 standard deviation, so the mean must be equal to 46. And just a note, when you see this mean is usually a population, and then capital M is usually a sample in terms of what the notation looks like in statistics. All right, so learning check. For a population with a mean of 50 and a standard deviation of 10, what is the x value corresponding to z equals 0.4? So take a moment, and hopefully you jotted down that formula, and take a moment to try to calculate that out to figure out what the x value is. And that answer is 54. Decide if each of the following statements is true or false. True or false, if the mean is 40 and 50 corresponds to z equals 2, then theta is equal to 10 points. True or false, if theta, or standard deviation, if I say theta, think standard deviation, is equal to 20, a score above the mean by 10 points will have a z-score of 1. And pause me or take a moment, look it up, think about it, and the answer is false for both of these. If z is equal to +2, then 2 times the mean is equal to 10, so the standard deviation is equal to 5. If the standard deviation is equal to 20, then z is equal to 10 divided by 20, which is 0.5. That's how we get there with that formula. So some additional things, every x value can be transformed to a z-score. Characteristics of z-score transformation. It's exactly the same shape as the original distribution of scores. The mean of the z-score distribution is always 0. Standard deviation is always 1. The z-score distribution is called the standardized distribution. So here we have an entire population of scores is transformed into z-scores. The transformation does not change the shape of the distribution, but the mean is transformed into a value of 0, and the standard deviation is transformed into a value of 1. You can see how that happens between this one and that one because x is converted to z. So this figure goes as a nice graphical representation. Following a z-score transformation, the x-axis is relabeled in z-score units. The distance is equivalent to 1 standard deviation on the x-axis. Standard deviation is equal to 10 points in this example, corresponds to 1 point on the z-score scale. So all z-scores are comparable to each other. Scores from different distributions can be converted to z-scores. Z-scores, or standardized scores, allow the direct comparison of scores from 2 different distributions because they have been converted to the same scale. Other standardized distributions based on z-scores. The process of standardization is widely used. The SAT has a mean of 500 and a standard deviation of 100 points. The IQ score, I mentioned that before, has a mean of 100 and a standard deviation of 15 points. Standardizing a distribution has 2 steps. Original scores are transformed to z-scores. The z-scores are transformed into new x values so that the specific mean and standard deviation are attained. Note that the predetermined mean and standard deviation are arbitrary. An IQ test could be rescaled where the average is 50 or 1,000 or 1. Figure 5.9, the distribution of exam scores from example 5.10. The original distribution was standardized to produce a distribution with mean is equal to 50 and standard deviation is equal to 10. Note that each individual is identified by an original score, a z-score, and a new standardized score. For example, Joe has an original score of 43 and a z-score of -1 and a standardized score of 40. All right, let's do some learning checks. A score of x is equal to 59 comes from a distribution with a mean of 63 and a standard deviation of 8. This distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is the new value of the original score? So pause me, take a moment, use that formula, and you get 45. A score of x is equal to 59 comes from the distribution with a mean of 63 and a standard deviation of 8. The distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is the new value of the original score? It's 45. So looking ahead at inferential statistics, and you did a little bit of this with your infographic already. Inferential statistics draw meaning from descriptive statistics. They give us purpose and meaning behind the statistics. So, for example, if you work somewhere and there's all these sales goals that don't make any sense, you might want to look at what the mean averages of everybody and have something a little bit closer to the average instead of something that's so far away in the ceiling that it's not possible in terms of the meaning of how to coach and how to actually apply something that can absolutely work. The meaning would be inferring inferential statistics and figuring out a way so that you actually have a good, say, measurement or metric or goal for, say, employees, for example, based on descriptive statistics of what's happening. Inferential statistics are techniques that use the information from samples to answer questions about populations. Interpretation of research results depends on whether the sample is noticeably different from the population. One technique for defining those noticeably different is to use z-scores. This is a diagram of a research study. The goal of the study is to evaluate the effect of a treatment. A sample is selected from the population and the treatment is administered to the sample. If after treatment, the individuals in the sample are noticeably different from individuals in the original population, then we have evidence that the treatment does have an effect. Figure 5.11, the distribution of weights for the population of adult rats. Note that individuals with z-scores near 0 are typical or representative. However, individuals with z-scores beyond +2 or -2 are extreme and noticeably different from most of the others in the distribution. So, learning check. Last week, Andy had exams in chemistry and Spanish. On the chemistry exam, the mean was 30, and the standard deviation was 5, and Andy had a score of x equals 45. On the Spanish exam, the mean was 60, and the standard deviation was 6, and Andy had a score of x equals 65. For which class should Andy expect the better grade? What do you think? So, the chemistry exam, the mean was 30, standard deviation of 5, 45, he had a score of 45. Spanish exam mean was 60, and the standard deviation was 6, the score was 65. So it would be chemistry, and that has to do with the standard deviation being closer to the mean. Decide if each of the following statements is true or false. Transforming an entire distribution of scores into z-scores will not change the shape of the distribution. If a sample of n equals 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. Well, the first one is true. The location of each score relative to all other scores is unchanged. So the shape of the distribution is unchanged. The second one is false. The number of z-scores above or below the mean will be exactly the same as the number of original scores above or below the mean. If you have questions on anything, reach out to me. Anything that's not making sense with the concepts. Equations, reach out to me. Now, there's absolutely a master list of formulas posted in D2L that will walk you through what formulas to use, and we'll do a little bit of worksheet stuff today in class, which is some of the homework. I may explain all the homework or some of it, but we'll definitely jump into some z-scores in just a moment. All right, let's take a look at some z-scores. So, share, no, not that. It's wrong share. All right, so let's take a look at this. Okay, so you guys should be able to see this. So let's talk about z-scores. So we're going to look at the appendix. This is just looking at the tables right now. So we're going to work through the following exercise with me and write down what you see in the unit normal table. This will help familiarize yourself with the table. First things first, a normal distribution is symmetrical. Note that, so for this reason, no negative z-scores are listed in the table. So you won't see those probabilities above the mean are identical to those below the mean. So for our first one here, we are looking for column B. So we go into the appendix and we want to find area under the normal curve from a given z-score back towards the mean. So what you're looking for, you're going to go into your z-scores. You're going to enter the table. We'll do that with everybody. And we're going to just pull from the chart just to familiarize ourselves with z-scores. Absolutely that straightforward, that simple. So let's go into our z-scores here. So for the first one, first z-score, you're going to go and you're going to look where the probability is back towards the mean. So in column B is the area under the normal curve. And then the z-score where the probability back towards the mean is going to be point. It's going to be, yeah. So area back towards, so this will be 0.0000. Actually, that was the one that we're looking at, 0.50000. Our next one, 0.3413, we look for the z-score the probability back towards the mean is you should have 0.1587. And then the next one you want to look at for 0.3389 is going to be 0.1611. And you should be looking in the chart. Don't just copy what I have. You want to make sure the chart's correct, that I didn't look at it wrong, etc. So the z-score where the probability back towards the mean is for number 4 is 0.0495. And we'll use these more as time goes on, probably over this week, just because of the pace of the course, because of it being accelerated. And 0.4750, the area, the z-score where the probability back towards the mean is 0.0250. Now, if you're looking at this in the chart, just align that with the column. The next thing we want to do is in column C, you will see the area under the normal curve for a given z-score towards the tail. Locate the z-score where the probability towards the tail is. So this will be 0.000. There's no area between the mean and the mean, okay? That's why that's like that. Our next one will be 1.00. Our next one will be 0.99. 0.99. Our next one will be 1.65. So really the z-score we're looking at. Our next one will be 1.96. And then that takes us through that. So if you add columns B and C each row, you will get 0.5000. The total probability above the mean, the total probability below the mean is 0.500 as well. So the total probability or area under the entire normal curve is 0.5000, or like half plus half, which is equal to 1. So the next thing we'll do will be the probability sampling distributions right here. All right, so let's go back to our screen share. So let's say, suppose a researcher wants to learn more about the attention span of individuals in some hypothetical population. The researcher cites that the attention span, the time in minutes attending to some task, in this population is normally distributed in the following characteristics. 20, that's your mean, plus or minus 36 standard deviation. Based on the parameters given in this example, answer the following questions. What is the population mean? Well, the population mean is given to us, so that's very straightforward. The population mean is going to be equal to 20, okay? The next one is, what is the population variance? Well, since we know standard deviation is the square root, we take the square root to get to the standard deviation, and we have 36, we can just go backwards, which means that would be 6, okay, for that square root. The next one says, sketch the distribution of this population. Make sure you draw the shape of the distribution and include a mean plus and minus 3 standard deviations. Well, if we do that, we would sketch a normal distribution, so a regular bell curve, with a mean of 20, a standard deviation of 6. So if we were to sketch that, it would look something kind of like this. We sketch a normal bell curve. So this is our bell curve like that. We would put our mean right in the center, that would be 20. Okay, this would be a better, this would be a more balanced bell curve. And then you want to show 3 standard deviations, really each direction. And this could be, plus, this would be plus 3 standard deviations, and this would be actually minus 3, minus 2, minus 1. This is plus 1. And these are your standard deviations that we were talking about. Plus 2, So our next thing that we want to look at, let's go back to our screen share here. That we want to look at is, now let's say this researcher takes a sample of 4 individuals, n is equal to 4, from this population to test whether the attention span in this population is really 20 minutes long, attending some tasks. So what is the mean of the sample distribution for the sample size 4 of this population? The mean of the sample distribution is the mean. So that's just literally telling us it's going to be 20 again, because it told us in the beginning. So this one's really straightforward, okay? So our next one is, what is the standard error for the sampling distribution? Well, the standard error is, we're going to take, the standard error is going to be the variance divided by the square root of our population, which is our n. So standard error is 6 divided by the square root of 4, which is equal to 3. And then the next thing we do with the sketch and normal distribution, that's kind of the same thing. It's just we're going to show standard errors instead of standard deviation. So you would mark it like just like we have on the whiteboard, except you would be clear that you were showing standard errors rather than standard deviations. SE is used a lot for standard error. So we would do the same thing if you're drawing it, but then you want to show like what your standard errors are. So I would say SE, this would be maybe -1 and so on, -2, -3, and those are standard errors, okay? But just make sure that you're labeling these correctly. I'd probably say standard error. Or you could also do the, like that when you're labeling, and then of course to your other side to 1, 2, 3. And ideally you want to draw these really to scale so that there's the same amount of distance between each one when you're looking at that. And we'll go back to our screen share here. All right, so our next thing is based on, so we did that, we did the shape, that, right? Based on a calculation of sketch sampling, let me think, yeah, we did that. So our last one is, if a researcher takes one sample size of n equals 4 from the population, what is the probability that he or she computes the sample mean of at least 23? Note you must compute the z transformation for the sample distributions, then refer to the unit normal table to find your answer. So x minus m is equal to the standard deviation. And we have all of that. So if we go into our whiteboard here, so z is equal always to x minus m over the standard deviation. Well, we have that. We have all of that. So our x value was 23 minutes minus 20, I believe, right? 20 was our mean. And our standard deviation, I think, was it 6? I'm pretty sure. Let's go back and double check that. Oh, it was 36. So divided by 36. So that's going to be a little different. This would be 3 divided by 36. So want to do. So we'll actually skip that last one. Don't worry about the last one. I feel like that's a publishing error. I feel like that was not set up right. This is more z-score stuff in just a moment, and or some SPSS stuff. So let's do the SPSS or the z-score just a moment. All right, so the normal distribution is also called the symmetrical Gaussian or bell-shaped distribution. That is a theoretical distribution in which scores are symmetrically distributed above and below the mean, the median, and the mode at the center of the distribution. Most behavioral data approximate the normal distribution. Rarely are behavioral data exactly normally distributed. In a normal distribution, 50% of all data fall above the mean, the median, and the mode, and 50% of the data fall below these measures. In a normal distribution, the mean can equal any value plus or minus infinity. The standard deviation can equal any positive value greater than 0. Proportions of the area under a normal curve are used to determine the probabilities for normally distributed data. The tails of a normal distribution never touch the x-axis, so it is possible to observe the outliers in a data set that is normally distributed. The standard normal distribution is one of the infinite normal distributions. It has a mean of 0 and a variance of 1. The Z transformation formula converts any normal distribution to the standard normal distribution with a mean equal to 0 and a variance equal to 1. A Z-score is a value on the x-axis of a standard normal distribution. The numerical value of a Z-score specifies the distance or the number of standard deviations that a value is above or below the mean. The standard normal distribution, or Z distribution, is a normal distribution with a mean equal to 0 and a standard deviation equal to 1. The standard normal distribution is distributed in the Z-score units along the x-axis. The formula for the Z transformation can be found at the top of page 180 in our text. It can also be found in section 6.4. Try textbook. Actually, yes, 5.4. Well, let's not worry about where that's located right now. So the whiteboard formula, since this is not a live class, just to reiterate that one more time, you want to use this for this worksheet. I'm going to explain the examples to you, and then the problems you can do on your own. If you have questions, please reach out. Z is equal to X minus the mean, or you can write theta, you can write, this instead, all right? It's kind of the same thing, all right? Over the standard deviation. Just remember that formula. We'll walk through that. So what we can do is like here, and we'll delete that. All right, so a researcher measures the farthest distance in feet that free throws were made during a basketball practice of professional basketball players. The data were normally distributed, so think bell curve. Mean is equal to 10 and standard deviation is equal to 2. What is the score for X equals 16 feet? Well, because the mean is equal to 10 and the standard deviation is equal to 2, we can find the score X equals 14 by substituting these values into the Z transformation formula. 16 minus 10, so that was X equals 16, 16 minus 10, that was our mean, divided by our standard deviation is 3. Therefore, a score of X equals 16 in the original distribution is located at Z equals 3.0 in a standard normal distribution, or 3 standard deviations above the mean. Now, assuming these are amazing basketball players, calculate X equals 20 feet in your Z transformation based on the data provided above. If you follow the example and the formula I just showed you, you'll very likely get to the right answer, but I'll let you figure that one out by yourself. And you should, of course, create your own scenario where you might use this formula, or frame it from the example in the worksheet. Some more definitions and FYI. The unit normal table, which if you would like, I could post that. I might have some that I can post just to make that easier. That should be in your textbook towards the end, though. That is a type of probability distribution table displaying a list of Z-scores and the corresponding probabilities or proportions of area associated with the Z-score listed. FYI, to estimate probabilities under the normal curve, we determine the probability of a certain outcome in relation to all other outcomes. The steps for locating proportions are as follows. Transform the raw score X into a Z-score. Locate the corresponding proportion for the Z-score in the unit normal table. A sample of scores is normally distributed with M equals 10 and standard deviation equals 2. What is the probability of obtaining a score greater than 14? So what we do is we apply the steps here. Step 1, transform a new raw score to a z-score. We compute the z transformation. In this example, x is 14. Therefore, the z transformation is z equals 14 minus 10 divided by 2. Therefore, 14 minus 10 is 4. So 4 divided by 2, z is 2. Therefore, a score equal to 14 in the distribution shows in our textbook. Step 2. In this example, we were looking for the proportion of z equals 2 towards the tail. To look at the proportion located in column A in table C.1 in appendix C for a z-score equal to 2. The proportion towards the tail is listed in column C. The proportion greater than 14 in the original distribution is p is equal to 0.228. Therefore, the probability is p equals 0.228 of obtaining the score greater than 14, or if you want to make it in percentage form, listing this in percentage form would be 2.28 because you'd move the decimal over 2 places to stay percent. Now do the following under a sample of scores is normally distributed with mean equals 9 and standard deviation is 3. What is the probability of obtaining a score greater than 18? Follow my example. You'll very likely get the right answer. Then come up with your own. Or frame it from the scenario. Just make it a little bit different. FYI, the total area is 0.5000 above the mean and 0.5000 below the mean in a normal distribution, again equaling 1. Example. A sales team likes to send funny jokes around the office to break up the monotony of making outbound calls. The manager wants to know how mindful his or her employees are of staying on task. The manager develops a survey to track how often employees are off task. She reports that they spend an average of 6.4 plus or minus 2.4, mean plus or minus off task during the day. Assuming the data are normally distributed, what is the probability that employees in the study spent less than 8 minutes off the task during the day? So we start by transforming the raw score x to a z-score. We compute the z transformation. In this example, x equals 8. Remember that said z equals x minus m divided by standard deviation. Therefore, z is equal to 8 minus 6.4 divided by 2.4. Therefore, that is equal to 0.67. In the distribution example, 6.7, a time equal to 8 minutes is located 0.067 z-scores, or just half a standard deviation, over half a standard deviation above the mean in a standard normal distribution. In this example, we are looking for the proportion of the z is equal to 0.67 to the mean, and then we'll add 0.5000, which is the total proportion of the area below the mean. It is because it is 1/2 of the normal distribution, and in this case, we're using less than. To locate the proportion, we look in column A of appendix C probably, and we see that p is equal to 0.2486. Proportion from A is 0.67 to the mean in column B is p is equal to 0.2486. We add 0.2486 to the proportion of below the mean, 0.5000 to find the total proportion. Therefore, 0.2486 plus 0.5000 is 0.7486. The probability is 0.7486 or 74.86%. That employees spent less than 8 minutes off task per day. Therefore, the jokes lighten the mood, and it's actually working in this scenario. So now do the same math, the same formula I just showed you, where they spend less than 10 minutes off task per day, and then create your own scenario. Locating proportions below the mean. In the standard normal distribution, z-scores above the mean are positive, z-scores below the mean are negative. Because a normal distribution is symmetrical, probabilities associated with positive z-scores are the same for corresponding negative z-scores. Researchers are often interested in the depression across many different groups, which can be measured using the Beck Depression Inventory, or BDI-2. Individuals who experience chronic pain are one such group which depression is of interest to the researcher. Using data based on reports and published research, suppose a group of veterans who experience chronic pain scored 24 plus or minus 12, mean plus or minus standard deviation, or higher scores indicate more severe depression. According to conventions, the score of 13 is less regarded as a score in the minimal depression range. Assuming these data are normally distributed, what is the probability that veterans who experience chronic pain scored in the minimal depression range 13 or less? Step 1, to transform a raw score x into a z-score, we compute a z transformation. In this example, the transformation is 13. So Z is equal to 13 minus 24 divided by 12. Therefore, 11 divided by 12 is equal to negative 0.92. In this example, we are looking for the proportion toward the lower tail. To locate the proportion, we look in column A and we find Z is equal to 0.92. Remember, always positive with Z scores. In the table, again, the normal distribution is symmetrical. A proportion given for a positive Z-score will be the same as a corresponding negative Z-score. Proportion for a Z-score 0.92 towards the lower tail is listed in column C. Therefore, the proportion is P is equal to 0.1788. Hence, the probability is 0.1788 or 17.88% that a veteran given this depression measured the score in the minimal depression range, a score of 13 or less on the BDI-2. A quick note on percentages, move it over 2 decimal points to the right. That's how you go from the probability make it into a percentage. So now, assuming data in a new group of veterans is 26 plus or minus 11, mean plus or minus standard deviation on the BDI-2, calculate the score in the minimal depression range, probability of veterans with a score of 15 or less, assuming the scenario is 15, do the same steps I just showed you and are shown in the worksheet, then create your own scenario. Example 2, memory is a factor often studied in patients with trauma such as a stroke, in which it is possible that memory is impaired. One type of metric used to measure memory among stroke patients is the cognostat, which includes a series of tests with a higher raw score indicating more severe impairment. Use data based on reports, published research. Suppose a large sample of stroke patients scored 7.5 plus or minus 2.5, mean plus or minus standard deviation on the cognostat metric. Assuming these data are normally distributed, what is the probability that a stroke patient in the sample scored 4.1 or higher? So to transform the raw score to a Z-score, we compute a Z transformation. In this example, X is 4.1, so Z is equal to 4.1 minus 7.5 divided by 2.5. Therefore, Z is equal to 3.4 divided by 2.5. Z is equal to negative 1.36. This would be, of course, negative 3.4. That's how we got there. In the standard distribution, a score is equal to a score equal to 4.1 is 1.36 Z-scores or standard deviations below the mean of the standard distribution. In this example, we're looking for the total proportion Z is equal to negative 1.36 or positive 1.36. Then we'll add, well, negative 1.36 because it's to the left. Then we'll add 0.5000, which is the total proportion for the area above the mean. To locate the proportion, search in column A in your appendix, and you'll find that the proportion for the Z-score shown in column B is P is equal to 0.4131. So we add that to the proportion of the area above the mean to find the proportion. So 0.4131 plus 0.5000 is equal to 0.9131. Therefore, the probability is 0.9131 or 91.31% that a patient in the sample. So now do the same thing with the example I've given you right here. So locating proportion between two values, assuming there was a study showing the possible benefits of playing games between study sessions on academic performance, let's assume the following. Adults who play video games between studying for their statistics course tend to improve 18 plus or minus 10 standard deviations the second time they take an exam. Assuming the data are normally distributed, what is the probability that a student who plays video games between study times will score between 12 and 30 points higher the second time he or she takes a statistics exam? Step 1, calculate X. X equals 12, transform a raw score to a Z-score. Do the Z transformation. In this example, X is equal to 12. The Z transformation is as follows. Z is equal to 12 minus 18 divided by 10. Z is equal to negative 0.06. So then we find X for 12. So we'll find the Z-score in appendix C and look for column B. Proportion to the two scores, we add 0.0239 to the second score where X is equal to 30. So we found this from column B in their appendix. So step 1, X equals Z, compute the Z transformation. Z is equal to 30 minus 18 divided by 10. Therefore, Z is equal to 1.2. Step 2, for x equals 30, the proportion between the mean of a Z-score of 1.2 is 0.3849 in column B. The total proportion of the 12 and 30 is the sum. So 0.239 plus 0.3849 equals 0.6239. The probability is 0.6239 or 62.39% that a student will score 12 and 30 points higher the second time he or she takes an exam. So now, calculate the probability that a student will score between 14 and 32 points higher before he or she takes this exam. Show your work, use the same formula as before. And that takes us to the end of what we're looking at in terms of Z-scores today in practice. But I'm going to walk you through the problem it references because I feel like that's not as clear as it could be. So I'll just video record that on SPSS. So give me just a moment to pull up SPSS, and we will do that next. And that will be our last exercise on this lecture. All right, this is our last thing tonight, guys. So we're going back to where we were earlier in the lesson. So we're going to do the standard error of the mean using SPSS. And then this, I just want you to go, maybe you just go to like stop when you get to crosstabs on this for the comprehensive tutorial document. And this I'm going to walk you through right now, okay? Because I feel like you might not see this, but what we're going to do is we're going to do a couple things. So researchers rarely know the value. Of course, we want to have our SPSS here. I can move that over. Okay, that's not letting me share. All right. So we're doing that last part of that worksheet, guys. And let's do desktop 2. Maybe do that. All right. Okay. So maybe we'll shut the camera off temporarily. Okay, so researchers rarely know the value of the population standard deviation, which is the numerator of the formula for the standard error. It is more common to estimate the standard error by substituting the sample standard deviation in place of the population standard deviation in the formula for standard error. SPSS makes the substitution to compute an estimate of standard error. The formula, which is discussed later, is as follows. The standard error, the mean, is equal to the standard deviation over n. I think I mentioned that earlier in class, but in case you missed it or I didn't mention it, the standard error of the mean is equal to the standard deviation over the square root of n. But you know, this is so cool. SPSS does it for us. So let's go back to sharing our SPSS here. And here we go. Okay. SPSS is designed to estimate the standard error using this formula. To illustrate, suppose we measure the individual reaction times in seconds for a team of 10 firefighters to respond to an emergency call. The reaction times are 93, 66, 30, 44, 20, 100, 35, 58, 70, 81. Let's use SPSS to estimate the standard error of these data. So click on the variable view tab like this and enter reaction time in the name. So go all the way to the top here and we're going to enter the words reaction time. Now, don't use spaces. SPSS calls those illegal characters and gets upset. Or we'll just say reaction instead of reaction time. So we're going to enter whole numbers. So we're going to do 0 decimals. Now, this is what we're doing. We're coding variables. Now, the next thing we're going to do is we're going to take the reaction time and we're going to enter these data. 99, 93, 66, 30, 44, 20, 100, 135, 58, 70, and 81. So we should have 93, 66, 30, 44, 20, 100, 35, 58, 70, and 81. And we enter those. Now we're going to do analyze, not chart. We're going to click on analyze, and we're going to go descriptive statistics. And then we're going to do descriptives. We're going to move the variable over here. We're going to click options, and we're going to go ahead and tell it what we want to see here, which is our standard error of the mean right there. You can ask for the other stuff too if you want. The standard error of the mean, click continue. That's what we want to focus on. Click OK, wait for it, and there you go. Mean standard error of the mean does it right there for you. And that means that it is 8.596, which is the same way as doing it by hand. The SPSS output table gives the value for the standard error is 8.596. We double check, and it also gives the value of the sample standard deviation statistic, which is right here. And sample size, when we enter these values in formula for standard error, we obtain the same result in the table. So do this by hand. You can do that by hand, like I showed you on the whiteboard a moment ago, or use SPSS. And again, just use the tutorials to do the second half of that. And that concludes our lecture for the day. So hopefully that was helpful for everybody, give you a better understanding of z-scores. Please email me, tell me when you want to meet live. If you do, call me, text me, ask questions, and I will see you either virtually in class like this or live if it works with the schedule of both of you. Take care, and I will see you in the next lecture. I hope you learned something. Have a wonderful evening.